Hello, and welcome to this video where we'll be doing even more leetcode. So let's continue with where we left off yesterday. So we were looking at subsets, and just before watching this video I watched it through. I've made this sheet here explaining it, and yeah, so now we're moving on to the next problem, which I think is combinations. I know that Python has an inbuilt combinations function from itertools, but we'll have to see how we can do that. So I'm just going to mute my mic here and watch the video. Okay, so the solution to this one is extremely similar to the combination solution, except from we don't return it when the length of the array is less than the length of, well, it's going to be, sorry, I'll get to the, it should be the length of k. So, combinations. Right. I'll try and do this from memory, then I'll just watch the rest of the video. So it uses recursion, well, backtracking, and we basically append it to our result, and then we also pop from the result. Okay. So yeah, and then we have the path, and then we're checking if it's equal to the length of path is equal to k, and yeah. So let's get started then. Result equals 0. So def backtrack start, and then this is the path. So here we can do if the length of the path is equal to k, then no. Result.append path, and then we can do for I in range. It should be 1 to, because it's 1 to n. 1 to k p dot append I think it's supposed to be I. And then also on that one we're supposed to okay. And in the code we're using this so that due to shallow copy versus deep copy. So here we're going to append I to the path, then we're going to go backtrack at I plus 1, then p and p dot pop to remove the last value. And I think that, no, so we don't need to return. Okay, so I think that's it for the function there. So okay, this should be start, and this should be k plus 1 because we want to include k. Is that right? No, n plus 1. Okay, yeah, so this is the solution, and basically what we're doing is well, at the start we have an array result which is at first got no values, and then we're going to call backtrack, passing in 1 and our empty array, and here we can have the backtrack function, and we check if the length of our the current array that we're making, if it's equal to k and we want it to be of length k in order to add it to our result, we do add it, and then we just return, so it's not an infinitely recursive function. And then we go through each of the values in a range of start to n plus 1, and it's n plus 1 because we want to include n, so that, yeah. And then we append I to p because we're adding to our array. Then we're backtracking on the p to get, say if I was the first value, then we want the rest of the values, so we backtrack on all of them. So for example, we get 2, 3, and 4, and then we pop off it, so instead of 1 we would get 2, and yeah, it would go like that. So then we go from 2, and then we get 3, 4. Sorry, 3, 4, and then we go to 3, and then we get 4. And the reason we're only getting values that are greater than it is because we're going from the range of start to n, and start increases every time. So yeah. So now I'm just going to write this up. Start path. Here we do if len of path is equal to k, then we do result dot append path. We just return. We do it for n in range start to n plus 1, and we go, let me just look at this code. So yeah, so the reason it's n plus 1 is because we want to do it in the range 1 to n, so inclusive. So in Python, it would never get to n plus 1, but it would get to n, so that's what we need to do. like that. Okay, so here we do path dot append. Sorry, this should be I. Then we can do backtrack I+1 path. Then we can do path dot pop. Then we simply just return. No, sorry, this should be outside. Return result. We also need to call backtrack. When we start off with 1 due to the range. There. Okay, and then that is it there. So it's quite hard to actually just go through it manually. So as long as you get the core concept. So now let's move on to the next one. Okay, so I've just finished watching that, and basically what you do is very similar to the other one. So I explained it here, and I was just going through it, writing down on the paper. So now we're on 46 permutations. So yeah, let's go and see what this is about. Okay, so first, before looking at the solution, I'm just going to try and do it myself. So he said it would be very similar to the combinations one. So 46. Right. So we're going to have our backtrack as normal. So start and then our path. And I'm just going to go like that for now. Result equals, I'm going to call backtrack. Okay, so we're going to start at 0 and that, and return result. So here we can check if length of the path is equal to len nums. If it is, then we're just going to do results dot append path. We're going to return. Otherwise, we're going to go for I in range. No, so for I in path, we're going to well, in the last solution, what we did was we did path.append I, and then backtrack. It'd be, wait, no. 1, 2, 3, 4, 5, 6. Is there a formula for how many possible? I'm gonna look it up. Formula. How many possible? This probably won't help because it's recursive, but okay. N factorial of n minus r. Okay, let's just say. Okay, well, it's not going to be I because. Okay, I'm going to do range path. Path at I, and then I'm going to backtrack at I plus 1 on path. Yeah, we need to do this. Then we do path.pop. Okay, so let's think about this. So I'm just gonna jot some ideas down on a piece of paper. Okay, so we've got our 1, 2, 3, and okay, so we start off with our array with 0 and the array. So go for iron range, the length of the path. Okay, so this does nothing. Length of the path. Okay, so do we need to first have I'm just going to run this and see what we get. So I don't think it's not going to have anything. Should be unranged and numbers. What? Okay, right, this is getting every combination. And it's having duplicates. So we can do if path I not in path okay okay, so let's see if we can. I think this might be too time complex, but ooh, let's go. We actually did one. Let's go. Yeah, this was very similar to the other ones. There's actually no change from the other one. Okay. So I'm just thinking. Unrange, yeah, okay. So that's why I need to change it. Right. So another. Well, is this a medium one? Let's go. Let's go, bro. Okay, so I'm just going to. Sorry for this paper, but you know I've got to keep it nice paper for the rest of it. Now let's write it up. So there's probably going to be a better solution, but you know we'll have to find out. Yeah, but this backtrack technique of appending, then backtracking, then pop is like so powerful. Like 3 leetcode problems just solved like so simply. Okay, and this problem's the last in the backtracking problems. So 1, 2, 3. Right, so I'm just going to watch the video now and see his solution. Okay, so I'm just watching this video, and he has got quite a different solution to me. So mine was almost identical to the one before of combinations. But yeah, so his solution is basically in the backtrack we have two arguments, so we have the start and the end. So instead, I passed in the path. So in the condition we look, if the start is equal to the end, then we're going to append the nums, and we're going to return. Then we're going to have a loop. So for unrange start to end, nums at start, we're going to swap the nums at start and the nums at I, and then we're going to backtrack at start plus 1, and then we're going to swap them back. And yeah, so I don't fully understand the problem yet, but I'm just going to watch it through, and I'm also going to write down my solution as well, because I think that was pretty intuitive. Well, compared to the other ones, as they're pretty much the same. Okay, so I'm just copying down the solution here. So, and then I'm going to copy down his solution, so left backtrack. Okay. Then we obviously need to call it. So what would it be? So we have the result equals empty array. Then we can call backtrack. It'd be 0 to len nums, I think it was. Then we just return result.
Purple line and the current index that we are on. We begin by looking up our numbers array and switching the start index with the current I index. So at this point our start is equal to 0, as is the I in our for loop. So switching these two numbers across keeps the current order in our numbers the same, allowing us to append the original order in a second. So we're going to call backtrack again, as always iterating up to the next index, and we're keeping our ending condition the same throughout. At this point our start is still not equal to our end, so we'll reach our for loop, switch numbers over and call backtrack again. So we have a new for loop starting at an I of 1. Our start and our I are still equal, 1 and 1. So our numbers list order stays as the original and we call backtrack yet again. 2 is still not equal to 3, so we reach our for loop, switching over the second index with the second index keeps the original numbers list order the same, and we call backtrack once more. At this point our start is equal to the end, so we can append to our results list a shallow copy of our numbers. So there's the very first permutation in our results, and here's where things begin to get interesting. Our code execution stops here and we go back up to the call stack to where we just called backtrack on the next index along. At this point our start and our I are still equal. We will see later that this line is meant to undo the swap that we done before the backtrack, allowing us later to make changes unaffected by our current changes in order to get the full list of permutations. So switching the 2 and the 2 gives us the original numbers list in the same order. We go back up to the beginning of our for loop, except now we've reached the end because our I will be 3. So our code execution can stop here and we can go back up the call stack yet again. At this point we had just called backtrack with the 2. So on the next line we will switch the I with the start, giving us the same order of our nums list. Then we go back to the beginning of our for loop and the 1 becomes 2. Now we can finally begin switching some numbers around. Our start was equal to 1 and our I is now 2. Switching these two numbers across will give us 1, 3, 2. We're switching the first and the second index, 1 being our start variable and 2 being the current index. So after that, we call backtrack on our start, which is 1, plus 1 gives us 2, and our end is staying the same at 3. At the top of our new backtrack, our start is not equal to our end, so we begin a new for loop. At this point, our I is equal to 2, as is our start variable, so we call backtrack yet again, adding 1 to our start. As you can see, our start is equal to our end, so we will append to our results and return straight after. So we add our current nums list, which is 1, 3, and 2. Code execution stops here. Back up the call stack, we have just called backtrack, and switching the current start, which is 2, with the current I, which is 2, does nothing. So we have reached the end of our for loop, because at the next iteration, our I will be equal to 3. And we go back up our call stack once more to when we had just called this backtrack with the 2 and 3, and we reach the next line, switching over our start and our I. Our start is 1 and our I is 2. This reorders the nums list back to its original state. At this point, the for loop for our backtrack with the start variable of 1 would have reached its end. So we go back up the call stack once more to record the backtrack with the start of 1 and the end of 3. Our I is equal to 0, as is our start, so switching these numbers over does nothing. And now we can finally loop over to the next iteration in our very first for loop. And taking a loop at our answer, right now we have 1, 2, and 3, and 1, 3, 2, which is the exact same as what the output has. So you know we're on the right track. And you can see that iterating now to the next index in our main for loop, the 1 pointing to the 2, gives us a whole new set of permutations beginning with the number 2. And finally, on the last loop, our very first index will have the number 3. So with this main for loop dictating our permutations and the order of our output in our results variable. So I'm going to leave it here because I'm pretty sure you can get the hang of it by now. If not, feel free to continue following the code execution by yourself. As for the time and space complexities, it is O of n times n factorial. There are n factorial permutations for an array of n distinct elements, and we've seen this before. For example, 3 factorial is 3 times 2 times 1. And for each single permutation, it takes n time to generate this to our results list. We are carrying out the same number of operations on our n factorial permutations, for example, swapping the elements and creating a copy of our list. So these n operations times by our n factorial permutations gives us a time complexity of n times n factorial. And similar to the previous questions, our space complexity is the exact same as our time complexity. We have our n factorial permutations, each of length n, requiring the same space to store inside our results variable. And on top of that, we also have a recursion depth of n space. So our call stack is O of n. And finally, we're also creating a copy of our nums list, which at each time we are appending to our results will be of length n. So that also needs n space. Overall, however, the bottleneck is our n times n factorial space, the most dominant term. And so that's it for our permutations question, covering all the different types of backtracking solutions we have, giving us one more solution in the same style we've seen before that we can reuse whenever we are asked this style of question, making changes based on the details that we are asked. And so that's it for our backtracking section. Our next section is linked lists. We have one.
Oh, I didn't mute my mic the whole time. Oh, my bad. Okay, so yeah, as you probably heard from the video, we're moving on to linked list now, and we completely finished the backtracking topic. So yeah, okay. So I might leave this until next time. So thanks for watching, and I'll see you in the next video. Goodbye.